Dear students, in this session, we are going to discuss about controllable phase variable form of state model. Let us see. A controllable system can be represented by a modified state model called the controllable variable phase variable form. It is obtained by transforming the system matrix A into a phase variable form. That means into a Bush form or companion form. We know that the state model of the system is represented by the equation x dot equal to ax plus bu, y equal to cx plus du. That is the basic equation. Here, in order to convert this state model into controllable phase variable form, we are using a transformation z equal to pz into x. So by using this transformation, we can convert this into controllable phase variable form. Okay. So here z is equal to pz into x where z is called transformed state vector of the order n by 1 and pz is called transformation matrix of order n by n. Z will have different variables such as z1, z2, etc. up to zn, and pc will have entries p11, p12, p13, p1n, etc. up to pn1, etc. up to pnn. So the derivation is that we know that z equal to pc into x. That is a transformation we are using. Here we are multiplying it with pc inverse. So we will get pc inverse z into pc inverse pc into x. And here this will become 1. So we will get x will be equal to pc inverse into z. So if we are differentiating this equation, we will get x dot equal to pc inverse into z dot. So this is another equation. So x is equal to pc inverse into z is one equation and x dot equal to pc inverse into z dot is another equation. We can substitute this equation into this equation. So that is state equation. So that is state equation and in the output equation. So we will get pc inverse z dot equal to a pc inverse z plus bu equal bu and y equal to c into pc inverse z plus du. So we can find if we are multiplying this by pc, we will get a z dot equal to pc into a pc inverse z plus pc bu, y equal to c pc inverse z plus du. Here we are making some substitution, that is this pc into a pc inverse is equal to ac and pc into b equal to bc, c pc inverse is equal to gc. So we will get a z dot equal to ac z plus bzu, y equal to cz z plus du. These equations represents the controllable phase variable form of the state model. Okay. So in this you know what is AC. AC is equal to PC into A PC inverse. So in order to form this controllable phase variable form, you need to find AC, BC and CC, and AC is obtained by this equation, but you know you want to find out this PC matrix, that is transformation matrix. So next step is to find the transformation matrix. Before that, here the AC is a matrix in the controllable phase variable state model, and here AC will have a form like this. So you can see here that its first entry is 0, second entry 1 and all entries are 0. You can see that this is in the companion or Bush form. That means the first entry is 0 and the next is a diagonal matrix and the last row will the negative quotient of the equation. Okay. And BC is all entries are 0 except the last entry. CC is C11, C12, etc. up to C1. So this is companion form or Bush form. That means we are converting the original system matrix A into a companion or Bush form in order to get the phase variable, controllable phase variable form. Okay. Next we want to find out PC. To find the PC, we know that PC equal to this matrix. Let us express it as P1, P2, etc. up to Pn. That means n by n transformation matrix Pc can be expressed as n number of row vector matrices. Okay. So next we want to find P1, P2, etc. So P1 is first entry will be obtained by Pc equal to P1, P1a, P1a square, etc. up to P1a raised to n. And here P1 is obtained by 0, 0, 0, 1 QZ inverse. So this is the equation for P1, and here we need to find you can substitute this P1 here. Similarly, here also you can substitute this P1. But here, in order to find the P1 value, we need QZ. Okay, the composite Q matrix, that is QZ will be equal to B, A, B, A square B, etc. up to A raised to n minus 1B. And here it depends upon the number of entries, depends upon the order of the matrices. So QZ is equal to B, A, B, A square, etc. up to this matrix. So this is the way we are finding the controllable phase variable form. And here we have find one method to find PC. There is another method also. So in the another method of finding PC, we can first of all we want to find out the eigenvectors, or eigenvalues, eigen equation or characteristic equation. For that we are using the matrix A. In that we can find the characteristic equation as lambda I minus a. So you will get an equation like this, and you have to substitute it equal to 0. And here you will get an equation starting from lambda raised to n to an. And here you have to note the quotient of all these equations. And by using the quotients, you are forming a matrix. We are calling it as a W matrix. And its entries will be, this is an minus 1, last quotient. And it will be next, second last, third last, finally A1 and finally 1. Next you will start with this one. So you will go like this. So the entries will be like this. So W is the matrix obtained from the quotient of this equation. And next you want to find PC. PC is obtained by QZ into W all inverses. So you want to find QZ. QZ is obtained by the equation B, A, B, A square B, etc. And PC inverse is obtained by QZ into W. So once you get QZ, and you will multiply that QC with the W. So you will be getting PC inverse. And also you may get PC. And finally you get QC. Once you get the QC value, you can substitute that value in this matrix. So PC is equal to P1, P2, etc. up to Pn is our required matrix. And that PC will have the value like this. Okay. So this is the way we are finding the controllable phase variable form. You can either use this method to find the PC, or you can use this method. Okay. That's all about this topic. Thank you.